Hey guys, well, Mr. Nicholson here. Just got done deleting the last video I was making because here I was going through this whole what I thought was the Unit 4 review sheet, and it turned out I was actually going through the Unit 4 assessment. So wouldn't that be funny? Mr. Nicholson makes a video that walks everyone through how to do the entire Unit 4 assessment. But seriously, so I deleted that. I'm starting over here. What I do have for you though is the Unit 4 review packet. I'm going to go page by page. It is 6 pages on paper. There is a Desmos slide deck that is kind of answer key, but even that I feel like isn't always super helpful. Just because I know the answer to that question doesn't mean I understand how I got it. So the other thing is not feeling super hot myself here. I know a lot of people have been sick. Um, my whole family pretty much has gone through the ringer on that one, but it's finally my turn. So I'm not feeling super great, but if I don't feel well enough, I've got this video for you. But honestly, even if I am there tomorrow, I'm still happy to make the videos because it'll be nice for you guys to be able to review all the information over and over up until Wednesday. So without any further ado, let's kick this thing off. So. First standard, understand similarity, side ratios, a little bit about definitions. So let's look at some definitions. Question 1, why are triangle ABC and FED similar? A couple reasons. The easiest one is to say, hey, look, they have designated angle A in this triangle, angle F in this triangle is similar, and angle B here is 90 and E here is 90. So what I have is two angles that are congruent. And that means that when I find angle C in this triangle, it's going to be the same as D in this triangle because they all add to 180. We have what we call the angle-angle triangle similarity theorem. And if you just called that out, that would be enough to explain yourself and justify why they are similar, is by the angle-angle triangle similarity theorem. The other one would be the definition of similar triangles is that you can take one triangle and through transformations and dilations, so translations and reflections and all that, scaling it up and down. If I apply enough of them, I would get one triangle to be exactly the same as the other, where the points lie on each other. I had previously mentioned that we also have the question answer key on Desmos. So this is question 1. Rather than typing any answers in, I just thought it'd be fun to, I don't know, maybe you guys, have you ever done that before? Use the keyboard symbols to make fun little pictures? No? Okay, probably just me. um, so anyways, I just wanted to preview that saying, hey, if you look at Desmos, the definition, the reason for question 2 is all there. If I go to question 2 is asking for proportions. So finding the measure of AC. Okay, well, AC is pretty straightforward, honestly. I've got several ways to do this. The easiest way is that I have memorized the Pythagorean triple. 5, 12, 13 is the Pythagorean triple. The other shorter way is to use the Pythagorean theorem, say 5 squared plus 12 squared, and take the square root, and you get a square root of 169 is 13. And there you have it. I would not use proportions. However, the second one, DE, asking for this side over here, DE, I would use proportions. In fact, I would say that, to get from the small to the big on the vertical leg here, I doubled. So now I know that the small one's 12, so the big one must be doubled to 24. So if we do that, let's check our work here. Go back to the yes, okay. Back to Desmos and our amazing snowman. But we're on question 2 here. We check our work. There you go. So again, Desmos is kind of handy. Let's see, 4.5 minutes. We're doing fine. Moving on. Woof. Okay, question 3. We're kicking it up a notch here, people. What we have is move this around a little bit. Use pen. And I'm going to redraw triangle number 2. What the heck? Amazing artwork. If I turn that up on its side, that leaves that corner up there as theta. So all I'm doing is taking this guy here and I'm kind of like rotating it around so that it looks similar to the x and 2.4 triangle. So again, I always like to draw things in that orientation so that they're all lined up and look the same before I start messing with sides, because if I don't, I might get the wrong side ratios. Okay, and that disappeared. Hold on. It's fun trying to edit on the fly here. So we're rotating it around so that this also, by the way, that's theta up there. I do not have a pen. I think I left it at the school, like a touch pen for the screen here, so I'm doing my best. But if I set these triangles up so that they're in the same orientation, that top angle above x here is theta, just like it is for, like, this is me redrawing that triangle there. So by the time I rotate the right triangle so that it's in the same orientation as the left triangle, we see that we have theta on the top for both of them. Now, what I was going to start to do was, so I'm going to call out the tangent ratio for theta, which we know is opposite over adjacent from our reference table. For theta, it tells us tangent theta here is 3 over 7. So 3 over 7, that means that this triangle here is 3 over 7. If we know that they're similar triangles, then I know that if I took 3 over 7 for my bottom, or my right triangle, whatever that 3/7 is as a decimal, that's going to be the same for the 2.4 divided by x. So the same ratio, opposite of adjacent, so new color. Cool. So I have 3/7 is my side-to-side ratio for my right triangle, but they're similar triangles. So no matter what, this ratio is going to remain the same. So 2.4 over x is going to be the same thing. All I'm going to have to do now is cross multiply. So 3x is equal to 16.8. So that x is about 5.6, I believe. So again, go to Desmos, check it out. Next slide. Oh, hey, look, I already did it. But there you go. Another question down. Let's see how we're doing for time. Yeah, we're fine. Anyways, that's the goal. Like, if they give you two triangles and say they are similar, then we can use that idea of the sine or cosine tangent ratios. But we can also still go back to the fact that if I have 3 over 7 for the tangent of one triangle, then that has to be the same tangent for the other triangle, as long as we're referring to the same angle, in this case theta. All right, number 4, use the table of ratios. That's a lot of information. A, using above ratios. Woof. Okay. Take a second, pause the video. I don't care. I'm not going to sit here and read through the whole thing. I would like to be a little more efficient than that. So pause the video if you need to. Read through the entire instruction if you need to. But once you do that, pause me right now. Okay, now unpause me. And we are going to answer the question for A. It says, long story short, you're being given the decimal ratios. This is the table that we've been working with. It says, if the opposite leg is 9.7, the adjacent side is 2.6, the hypotenuse must be 10. And that's all, again, from reading. Hopefully you make sense of that. If not, please come see me. The question they're asking is, identify another set of potential distances for the sides of triangle ABC. Well, if we're being perfectly honest, when they say, oh, give me another similar triangle, or give me 2 or 3 similar triangles, you guys, all they're asking you to do is come up with another list of sides that would make a similar triangle. Well, what makes something similar is that they are congruent angles, and then the sides just have a scale factor. So For 4a, I'm just going to take 9.7 times 2, 2.6 times 2, and 10 times 2. I just doubled those sides, and that is a set of potential distances for the sides of a new triangle, right? Couldn't tell you what they are, but I don't have my calculator in front of me at this very second, and also for efficiency, double your sides, triple the sides, I don't care. Multiply all the sides by 1.75. Either way, you have a potential distance for the sides of another triangle. B, how are my triangle and your triangle related? Okay, this is where it gets a little bit more nerdy, triggy, and so on. How they're related is that if I took my triangle, here's my triangle, here is your triangle, it's over here. Okay. Actually, I have to go backwards. That's you, and that's me. I say that because I doubled it. My skill factor was 2. How are they related? Well, the relation is that if I go in and say, I'm going to pick this angle right here. Oh, that is disgusting. There we go. Let's try that. I'm going to pick that bottom right corner, and I know that they're congruent because they're similar triangles. If I'm going to use that as my theta, that's the angle I want to focus on. If I want to focus on that and say the sine of my theta versus the sine of your theta, the sine of theta for you and the sine of theta for me, they're going to be equal. That's how they're related. They're related because I'll do, let's call it a 30, 60, 90 triangle. Okay, magically oh, hey, look, it's a 30, 60, 90. I've got 1, we'll go 1 on this side. We double that hypotenuse, and the square root of 3, horribly drawn in there. I doubled that, so mine is 2 here, 4 here, and 2 square root of 3 over here. Going back to the original question, how are they related? If I took sine of theta, for you, that would be, we change the color one more time. For you, that's 1 over 2, opposite over hypotenuse. For me, that is 2 over 4, which equals 1/2. So, and that wouldn't change for any size of triangle as long as they are similar. I would get that same ratio. Okay, I'm gonna stop there. I have no idea. I can't even see the clock on my little timer here, so I'm gonna stop there. I'm gonna make another video. Just keep rolling.